What would we do without coffee? Unreal. Isn't it? Oh my God. Okay. Calculating the electrical load. You guys have we have gone through an example, really good one yesterday and last week over step-by-step load calculation. We're gonna go over this chapter, and you guys will do, I can't remember, next week or one of the weeks, you will be doing complete load calculation with a template that your friend Chad will be giving you about load calculation. So by the time you do it 3 times, Gary, if you don't know it, then you and I have to meet me down that parking lot, and if I don't show up, just keep waiting there. So meaning you have to get it. Keep picking on Gary today. Okay. You can tell it's Friday, huh? Yeah. All right. Monday, you guys are coming. I'm not. Lighting loads. You guys remember when we did the load calculation? We summarized it very simple, right? When we did the load, we said number one, when you do the light, we have lighting, so you have to worry about your lighting. You guys remember that? And then we went to receptacles. Number three, number two, and they don't have to be in this order. You guys remember, they don't have to be in this order. And number three, the chunk of these are what I call them, Alex. These are chunks of loads. Every building you walk into, there will be a chunk of load for lighting, a chunk of load for receptacles, and there will be a chunk of load for mechanical equipment. This includes the heating/cooling system, right? The mechanical equipment, your heating, cooling system, and that you have to do. That was the chunk of load. So basically, that's for the most part. These are the 3 major chunks of loads that you walk into any building and you'll find these. And a fourth one would be owner equipment. Fourth, I called it. You guys wouldn't have it. Owner equipment. Motors, I listed them under mechanical equipment. Mechanical equipment, guys, for the most part, they're 2 parts. Motors and HVAC. Which is HVAC is a special type of motors. These are, they call them mechanical equipment. All the pumps and exhaust fans. Pumps and exhaust fans go under motors. The chiller and the heating element, the chilling and heating goes under chilling heating. Both of them go under the category of mechanical. For our load calculation, guys, we split them slightly, but they typically go under mechanical equipment. Owner equipment, the owner equipment, John, is what happens if you own a data center? What if you have a room like this full of computers crunching for your business, right? Crunching numbers. These are special data owner equipment. Another one that would be, what happens if you have a manufacturing building? You do things, you manufacture things. Where would you put the equipment, the machine that you have in your manufacturing floor? Where would they fit among these 4 types of loads? Well, mechanical means, typically when we say mechanical, we mean heating, cooling, and ventilation of the system. That's what mechanical, guys, typically means, because every building needs to be heated, cooled, and ventilated, right? Every building needs to be lit. Every building needs to have receptacles so people can plug loads into. So when we have owner equipment, if you're a pharmaceutical company and you're making drugs or whatever, these are called owner equipment. Because the equipment for the owner, right? They are mechanical equipment ultimately, but they don't cool or heat or ventilate the system. Any question, guys, what these? So these are the 3 types of loads. You're going to 4 types of loads for the most part you're going to encounter. So that's what we're going to be talking about. Exactly the same thing here. Here's my receptacle. Here's my lighting. Minimum equipment loading. We'll talk about this one. Determine reasonable connected load. Tabulated and unbalanced load. There's something called the demand load, design load, and connected load. You guys will hear this one all the time. In a second, we'll explain what is a connected load. If each one of you guys is, okay, connected load, look at these fixtures. If each one of these fixtures is pulling 200, let's just say 100 volt amp. The connected load is you add these 100 amp together, okay? And we'll talk about the design and the design loads and the demand loads in a second. What did we say about continuous load, gentlemen? Anybody?
3 hours. Yeah, 3 hours.
3 hours or more. And what do you do to the load if it's continuous? Immediately from the get-go, you up it 1.25 immediately. You multiply it by 1.25. Why? Safety. That's all. Continuous load. Non-coincidental load. Do you guys remember saying about something about non-coincidental load? Anybody can give me an example of non-coincidental load? Non-coincidental means they don't exist at the same time. Look at the building. What is the major load in a building that does not exist? Thank you. Heat / cool. You don't start your air conditioning and your furnace at the same time. So you don't heat. So what do you do in coincidental load? You pick which one? The larger of the two. You pick the larger of the heating or cooling. And that's what we did, guys, for you. Okay. We talked about that. So this is just a quick introduction. National Electric Code, guys, is the Bible. When I was walking you yesterday through the sheet, have you guys seen that I was referring you to tables and highlight this? And that's the law, the electrical law. I can tell you anything I want, Gary, unless I substantiate it by the NEC code book. It's Chad Curdy's opinion, which is basically, for the most part, you tell it to your employees, they're worthless. It's his opinion, right? So the difference between an opinion and a fact in the electrical industry is referencing it into the code. Now, when you're referencing in the code, it becomes a design fact, basically, right? Because a group of people have put the code together, a practice from all 50 states, all the smart people all over the US, put this document together. So they're definitely much smarter than me individually or you, right? That's why we have this document that we call the code. Okay, why do we have it? This is the practical, they call it practical safeguarding of the electrical system and adequacy. So when we have the NEC code book, guys, the main reason for having the NEC code book is to have the safety of the people and equipment. Meaning, I don't want you to get electrocuted and die, or die in an arc flash, and I don't want to burn the building. That's why the NEC code book is there. I have a friend of mine. He always says, guys, you're designers, you're not electricians. So when you work as a designer, you guys remember the reference point here, 0. Here's the scale of, this is excellent, this is poor. Excellent design, this is poor design. This is the 0. Cool. Now, the higher you go, I'm going to start my curve here. The higher you go, and what is this one here? This is 0 point. So this is, I call it the NEC. So when you design your building to the NEC code, you're sitting at what point? 0. Do you see now why Michelle Cooley-Erickson, you know, they say when you tell them that Chad is doing all this calculation, say, we're going to up it. Designing the NEC code book is what? 0. If you go below the 0, where are you? In which territory? And not poor, violation too. I have to add violation. Violation of law. You have, it's not a felony, a misdemeanor. You're in the misdemeanor area. Literally, you go below the code, you are in breaking the law, electrical law. And I'm not saying that, I'm not joking, it is electrical law. So if you burn the building and they bring somebody like Chad, pay him $150 an hour to go to the court, witness expert, I said, hope he didn't use 220.12, right? He used 2 volt amp per square foot instead of 3. And the judge, I refer it to the judge, and guess what? I become the star, and you go to jail. So this is where if you go below the NEC code book, where you are in violation of the law. Now, if your design is excellent, what do you need to do? Go above and beyond the law. So if the NEC code book guys allow you to put 10 receptacles in a circuit, would you put 10 receptacles in a circuit? No. Okay. So that's what the engineers do. If they allow you to put 10 receptacles in a circuit, they end up putting 7 receptacles in a circuit. Allow 3 for future. That's where you become in the excellent area. Though there's a happy medium. If you keep going up here, you know, there's a point at this point here, guys, in the excellent department. I'm going to put it in that here. You know, if you keep going in that area here, it becomes uneconomical, non-feasible. So you're playing a rule where you're going to be in the excellent area, and at the same time, you don't want to overkill. You know, how do you overkill? Every receptacle right here, you bring a branch circuit to it. Are you crazy? You know how much money you're going to pay for that one? Now, if you put 4 or 5 of them in one circuit, good industry practice, you know what I mean, versus 10. But you put each one of them in one circuit, you have to justify it. How do you justify it, Jay? Say, well, Chad, I know a vending machine is going to be on this receptacle. Check. Great, right? This is just a convenient receptacle sitting like this, and you give it a dedicated circuit. Ooh, you're getting into that area where you're overkill. Am I making sense, guys, in terms of the design? 0 point is NEC code book. Violate, that's why we use it as a reference point and you build on it. Okay. So when you're doing your calculation there, you have to take into consideration guys the future growth with the building growth. And a lot of people go above and beyond what the NEC code book good allow you to. And that's, you guys are right in here in the consulting engineer department. So if you leave Chad, and when you guys were circuiting, like I said, 10 receptacle per circuit, and you go to an engineering firm, they're using 4. That's not wrong. Remember, they don't want to be sitting on the 0 point. 0 point. Now, if you work for electrical contractor, he's not here. When you work for electrical contractor design, now those guys push the envelope a little bit. The engineers tend to push the envelope up. The contractor tends to push the envelope a little bit where? Down, closer to the 0 point. Why? They want to make money. They want to make money. And you guys as a consulting engineers, that's where you sit. You sit somewhere, you need to balance between the two. You know, you're pushing up and the contractor pushing down, and you have to find this happy medium. None of you will cross the red line though. Nobody wants to cross the red line. The red line is you go violate the law. Am I making sense? The law is the 0 point NEC, and you and the contractor pushing each other. So a couple of examples, guys. If you don't tell them how to circuit, and you don't tell them how to circuit, how many receptacles in a circuit to the contractors, well, guess what? They're going to go follow the law. Where was the law? 10 receptacles per circuit. That's cheaper for them to do it, right? You didn't tell me how to circuit, and I met the code. I met the law. That's where we come to push the envelope, and I'm bidding it, so I need to make money. So there's interest group. So please be aware of that one. We, the engineers, we plan for future growth. That's why you put yourself in an excellent design. Don't overkill. Don't overkill. A good example about overkilling versus guys overkilling. A good design is to grab, you grab your conduits, and if you have mechanical equipment, a good design idea, when you have mechanical equipment, air unit, chillers, and what's not, 1 pipe per mechanical equipment. Okay, that's a good design. Now you're in the excellent design. Now you go a little bit lower. Well, there are 2 pieces of equipment by each other. Can I group them together in 1 pipe? Yes. Now you went slightly. You're not violating the law, but you went cheaper, right? Cheaper pipe. You put 2 circuits in 1 pipe. Is it violating the code? No. Cheaper. So that's what the contractor tried to do. Group them together and shoot the cheaper installation. So we try to push a pipe per equipment, mechanical equipment. So if you have what we do is when you come out of that panel, with a 3, typically we go 3/4 of an inch out of that panel on the top, and you send, remember that 8 conductors that we did the calculation for? So you come up with 8 conductors, which give you 6 circuits, 6 20-amp circuits coming out of this pipe. Okay, that's another idea that a lot of engineers use, which is a good idea. Now some contractor might push 12. Now you want to say no more than 6 circuits and 1 3/4 of an inch. That's your engineering specification. So you don't want to push more than that. So anyways, that's kind of where we're going above and beyond code, guys, and planning for the future. Okay, so determine the load in electrical. So your job, guys, is like I said, when you determine the load, I told you guys that yesterday. Your first job, Jay, is to find the service, and we did it, right? Remember that service panel? The second is to find the feeders. Remember these feeders going to the receptacle panel, lining panel? We did that. And the last thing we do is what? Branch circuits. We didn't talk a lot about branch circuit or load calculation. We will be doing branch circuit for lights, branch circuit for receptacle, branch circuit for equipment, guys. But your load calculation must be able to answer what size of panel do I have, what size of feeders do I have, and later on, based on the load, what branch circuit do I need? How many branch circuits do I need? Can you guys see that? Service, feeders, branch circuits. You typically have one service, typically one service. Feeders, you probably, depending on the building, you could have from 10 feeders, depending on the building, into 100 feeders coming out of different panels. So feeders could be a lot, okay? So this is typically a number of feeders, typically one. Branch circuit, typically depending on the size from 10 to 100, you really have to have, when you have from 10 to 100 feeders, we'll have a huge building, really huge building to have 100 feeders in it. And remember, Brandon, at Mishad Cooley, they call the feeder, some branch circuits feeders, so be very careful of the term. A feeder is between two panels. A conductor going to the air handling unit is not a feeder. Even though a lot of engineers call it feeder, guys, right? Size the feeders. They are branch circuits. So can't mix them together. Now, for branch circuits here, guys, you can go in a typical building from 40 all the way to 1,000 branch circuits. These are all the ones, the little circuit breakers in the panels, and a little bit bigger for all the mechanical equipment, and the heating, and the cooling, and the lights, and the receptacles. Am I making sense? All of them must start with a circuit breaker. So ahead of this one, you need to have a circuit breaker. Ahead of every one of these, you need a circuit breaker or a fuse, and a service have to land on a circuit breaker or a fuse. And then you pull your conductors. Does it make sense? So that's basically what the load calculation will get you. The NDC code book guys give you, can I emphasize the word minimum load from the table? Does the NDC code book give you the maximum load? We said it's the 0 point. Below it, you violate the law. So keep this in mind. That's why a lot of contractors guys when they size pipes. So for example, if you have 4 conductors, and the 4 conductors is 3 conductors are 4/0 and 1 conductor is 1/0. When they size the pipe, they size them all for 4/0. 4/4, move on. Don't mess around with 3/0. Assume it's 4/0, right? Worst scenario, and move on. So a lot of people guys go a little bit up, but don't overkill. And again, NEC guys give you a guideline into how to do load calculation, and I'll show you a couple of things, and we already done through a few of them. There is, yes sir. Yes. The first thing when you guys do the calculation is you're going to ask yourself, what is the future planning of this building? As a designer, as an engineer. When we start you doing your calc, when you meet with the customers, what's your future planning for this building? Are you planning on adding to the building? Are you planning in adding loads to the existing building? Are you planning to add to the building another section? You take all this into consideration when you size your service. So if they're planning to add another 10% to the building, what do? You take your load, up it 10% for future expansion. From at the end, when you do the calculation, you came up with the size of a panel 600 amp. Multiply by 1.10 and size your service. That's how we typically do the whole thing. Because you're going to up it 10%, typically that's up the whole thing 10%, that will get you addition to the future. If that makes sense. Yes, sir. You on the feeders only. Future, when we do future expansion, guys, you size the feeders and the services for future expansion. For example, if I have to add another 5,000 square foot on the service, so the service have to take into consideration when you size the service, the conductors, the conduit, and the box have to take into consideration the 5,000 square foot addition. Then you ask yourself, well, how am I going to feed this addition? You have two options of feeding the addition, right? Either existing panel, pull branch circuit to the 10,000, not a good idea though. Or pull in a feeder to that area, feeder or two to that area, and feed that area separately from its own separate panel. And that's what most of the people do. If that's the situation, when you size your panel, guys, here's your service. What a typical engineer will do, they have, here's my panels, here's my panel, is my third panel. And right in here, guys, they have a spare conductor. They call it spare future. So you see what they do? In the main panel, they size the main panel, and a lot of them even put a circuit breaker there. So they know they need another panel to the addition, maybe two panels, unisize. So depending on the size, let's just say two. I have two for future. So these will be, let's say 225 amp panel each. This is 225 amp. Both of them, you just put the circuit breakers and say spares future. That's how they do them. So no pipe, nothing, just they're sitting right there. So when you expand, you bring your pipe to the box, the circuit breaker is sitting waiting for you, tie it to the end, and from the other end you put your panel and you're up and running. That's how we see them at Michaud, future expansion, a lot of stuff, and typically grade and dotted. They gray them, the future expansion, and they dot them, they put them in dotted, some engineering firms, and they write underneath them, future expansion. And yes, sometimes they put spare or space. There's a difference between spare and space. So if I say spares, these circuit breaker exist. If I say spares, what do you guys think? Means leave a slot for them. A space is a slot, no circuit breaker in it. Leave a slot equivalent to 225 amp to fit a 225 amp. You have to put the amps though, because the slot for a 15 amp circuit breaker. The slot for a 15 amp, this is 150 amp circuit breaker, guys. And this guy is 15 amp circuit breaker. Look at the slot. Do you think they fit in the same slot? Definitely not. So when you say space, you also have to emphasize what amp for the space. So space or spare? On your schedule, guys, I'm going to ask you to put a couple of spare circuit breakers for future use. Any comment about spare, space, future, and so forth? All right, do me a favor. I would like you please to go to table 220.12. We have been there. This is not new. Go to table 220.12. 220.12. Commercial book. No, NEC. When I say a table, guys, moving on, when I say tables, typically I mean NEC code 220.12. That's a lighting table. Now do me a favor. For an office building, what was the allocated volt amp for office building? Light, 3.5 volt amp per square foot for what? Lights. For lights, the code allocate 3.5 volt amp. Now the reason why you guys have done, we've done the calculation, so we're not going to do the calculation, but I want to bring to your attention a couple of things. Now, let's talk about the energy code. Energy code require you to two things when the energy code is, and a lot, we adopted the energy code in Minnesota, guys. Require you to, number one, have to meet certain volt amperes square foot, and number two, you have to provide an auto means of disconnecting your lights. And number three, you are to provide efficient equipment in your building. So, look at this fixture. I will provide an efficient ballast for this fluorescent fixture or LED driver for the LED fixture, the most efficient one. That's requirement one. Number two, I have to provide, so I can provide a volt amp that meets the NEC code book. And number three, these will not meet the energy code. Because if you guys left the room, the light will stay on for a long time. So what meets the energy code is an occupancy sensor, they call it. Now it's called vacancy sensor. They put it right in there, guys. You walk in, it hears and sees you. Most of them are dual technology. They can hear and see you, literally. So they send all these waves that can hear and see you. So if you're in the area, even typing will keep the light on. The minute, if you sleep and snore, it will keep the light on in an office. Literally, what you guys going to hear about the experts in this technology. If you move your eyes, it will keep the light on. So it really is. So the dual technology though, the dual technology, they can hear and they can see you too. So they have two technologies together. Anyway, you walk in there, as long as you're in the room, the light will continue to be on. Not just the lights, some of the lights. They might have, if it's a bigger room, certain lights where you're located. You leave the room, 15 minutes, typically 10 to 15 minutes, they shut the lights off. Energy code. So how does the energy code work with the building code? Well, look what happened. To meet the energy code, guys, for the most part, now the energy code, to meet the energy code, this is the NEC code book. NEC. Now energy code, the energy code for lights, you know how much they allocate lights for you? Anybody guess? 1 watt per square foot. 1 watt. The NEC code book, and by the way, for the most part, treat the watt and the volt amp the same. For the most part, they are the same. You know, so if to meet the energy code that you guys are designers, you have to design based on 1 watt. To meet the NEC code book, you need 3.5. So how am I going to do that? Right? So what happened is you design based on this, and you operate based on this right now. You design your building based 3.5, so it can handle up to 3.5. But when you operate your building, right? You can see the word operate. You operate your building based on what? 1 watt. So you guarantee to meet the energy code when all these lights are running and they're burning watts, and you calculate all the watts burned divided by the room, square foot of the room, you are 1 watt per square foot or less. That's how they do it. In 2014, so you design based on 3.5, operate based on 1 for most of these equipments. In 2014, guys, they allow you to design based on the 1 watt. And that was a major change in 2014 to acknowledge the energy code. So now they say the following. They say if you can see an exception right under that table. It says if you have a lighting control system. Do you guys remember what Joe was talking about, lighting control system? If you have a lighting control system, control your building. And monitor it, Brandon. It's monitored. So if it exceeds certain value, it will trip the circuit breaker. So you have to have a monitoring system that monitors, which is easy. Through a lighting control panel, guys, you can achieve monitoring your lighting system. If you install a lighting control system that can be monitored, which all of them can, then guess what? Then I can size based on 1 watt. Who cares? Let me tell you what who cares. Now, if you size based on 1 watt, the size of your panel will be a 100 amp panel. Now, Brandon, if I say 100 amp panel, you can tell me how much circuit and conductors and wires are going to be 100 amp panel. That's based on, this size is based on energy code. If you go based on NEC code, multiply this number by 3.5, gentlemen. So what would you give you? 350 amp panel. That's your NEC code. Do you see the difference? In terms of pipe and wire and conduit and so forth. Do you see the difference? For the same load, from 350 amp panel into 100 amp panel, if I use the energy code. Substantially less. 3.5 times less. That was changed in 2014, where they allow you, if you have a lighting control panel that you can control and monitor your lights, no problem, and you are installing it, which is not hard to do, and then to meet the energy code, you can say, well, here's the NEC code book. Remember that fancy stuff that I told you guys about lighting panel, and you came up with 350? Well, let's do the energy code 1 volt amp per square foot and see what you come up with. We typically come up with almost 1/3 of what the NEC code book, and size your cables and conductor based on that. So something to consider. Don't do it with me yet. We're still sizing. A lot of people's engineers still sizing based on the NEC code book and operating based on the energy code. That's kind of the practice. Any comments, guys, questions about the energy code versus the NEC code book? Energy code, and to meet a commercial building, we have an energy code calculation that we do in this building, guys, that we have to meet the energy code. Right now, the way we meet it is we design based on NEC code book, operate based on energy code. So, but now, can I design based on energy code? Yes, absolutely. Okay, you guys are looking at this table. This table gives you allocated volt amp per square foot for different type of occupancy. Show window, do you guys remember? I'm going to just go over these. Show window, anybody remember when we said 200 volt ampere square foot or linear feet, right? We calculated it. This is just a review of what we've done, guys. 150 volt amp for track lights. You guys remember that? For every 2 feet. This is from the sheet that we went over. Exactly the same calculation. For show windows and track lights. These are not general lights. These are special lights in addition to the general lights. Okay. The NEC code book, guys, also require you to have a receptacle outlet for the show window, each 12 feet. So if you have a show window and you calculate, we know how to calculate the show window, right? Show windows, we have 200 volt amp per linear feet. So, and when you design it, every 12 feet, you have to put a receptacle so they can plug in. Another 12 feet here, what do? Put a receptacle so they can plug these show windows. But the load goes by what? The load goes by 200 volt ampere square foot. These are just receptacles. And they have to be sufficient enough to, you can connect as many. You guys know that track lights, put track lights on these show windows, whatever lights you put on them. They have to be sufficient enough to power these lights. That's a requirement. Nonlinear loads. A fancy name for any circuit that feeds electronic equipment. Now, so my friend, can you think of any circuit that does not feed electronic equipment? Think around you. What's your laptop? What's your laptop? Electronic equipment. Digital electronic equipment. What's the driver in this ballast? 99.9%. Now, we don't use electromagnetic ballast. If you guys are familiar with them, they're coils. They don't meet the energy code. You have to use electronic ballast. What's an electronic ballast? Electronic ballast is, I call them electronic equipment, guys. They are sloppy eaters. You see, if you've seen your children when they're eating when they're young, right? The food goes into their nose, into their mouth, in their pockets, everywhere else. That's sloppy eater. Yes, sir.
Question about I was gonna put a rear. I know it's not off a battery source, but I was gonna put a rear LED taillight on my motorcycle. You guys said you need to install ballast.
Driver.
I didn't know anything about
It's not ballast, it's a driver. Well, it's like a ballast.
It was a little square thing.
Yep.
He says it takes such low energy that it puts all the high energy in the other part of the circuit on the wiring harness.
Yeah.
So
LEDs.
For other ballasts.
Yeah. Well, LEDs, as well as fluorescent lights, they need a driver. They call them the driver. The driver that drives them. For the LEDs, it takes the AC typically, the 120, and convert it into 24 volt DC and dump it across these LEDs. That's why you need that ballast for the LEDs. Now, for these guys, for the fluorescent, what they do, guys, depending on the type, they take the 120 and they convert it to different frequencies, and they fire these lights at certain frequencies. Long story short, they make them very efficient. That's the job of the ballast, to make the light very efficiently working. That's why they call them energy efficient ballast, electronic ballast. So they chop the frequency. So they're running them at not 60 hertz. They run them at thousands of hertz. The arc. Remember, this is an arc. They're arcing to create the arc and maintain the arc. So yeah, you need a driver to get you the DC for LEDs. You need a ballast to get you an efficient fixture and maintain, and run efficiently the ballast. If that makes sense. Okay, so nonlinear load, guys. Anyway, all of these we create on the neutral. They overheat your neutral. So long story short, they overheat your neutral. When you have a three-phase system, gentlemen, here's my three-phase system. And if you don't know a three-phase system, you are in a big trouble. This is my phase A, my phase B, my phase C, and a neutral. Okay? Typically, when you have a lighting circuit, guys, a typical application of a lighting circuit is to do the following. You take circuit 1, circuit 2, circuit 3, and a neutral. So, and this will be phase A, phase B, phase C, and a neutral. Take them together, and from the other side, here's light 1, light 2, light 3, And what they do is you feed the phase A to light 1, phase 2, light 2, light 3. And what do you guys think the neutral? Share 1, 2, 3, and share neutral. That's a typical application, the cheapest installation. A three-phase circuit with a neutral that they're sharing the neutral. And oh, by the way, I said one light here. Why don't you put 16 here, 16 here, 16 here? Each one of these circuits will have 16 fixtures like the one above your head on one circuit. Can you see coming out of how many wires? Coming out of this. This is what they're coming out of. 16 times 3 is what? 30, 40, 48 fixtures, gentlemen. 48 fixtures coming out of a set of wires like these. On 3 breakers tied together. It will be tied on a breaker like those 3 of these. They have to be tied together because they tie, but there's a hole here, they tie together. So these will have to be multi-wire braid circuit tied together. On 3. That's what they call it, multi-wire braid circuit. So long story short, if these lights have a ballast on them, then if this circuit is pulling 10 amps, this is 10 amps, this is 10 amps. Did you guys study the three-phase system? Okay. So what happens if you have a balanced three-phase system? 10 amps, 10 amps, 10 amps here. What do you think the neutral will carry? Big fat 0. It should. That's why we call it the three-phase system is superior system, because now that neutral is just sitting there carrying nothing. No voltage drop, beautiful. That's why we love it. Now, this is true if your equipment is not electronic equipment. This is true if these were motors. No electronic on them. It's true if it's heaters. The minute that you put electronic equipment in between, which is in this case the ballast, all these electronic printers and plotters, your laptop and mine, guess what the neutral, in this case, because they're sloppy eaters, the way they digest electricity like my babies, my son when he was a baby, food in his ears and nose, mouth, everywhere else, instead of just putting the food in their mouth. I call them sloppy eaters. Guess what's going to happen with the neutral here? It will carry 10 amps.
If they're unbalanced?
If they're balanced. They are still balanced, and you still carry 10 amps. The reason for this one, guys, because electronics, they manipulate the, I don't want to get into the, we'll get into the harmonic side. What they do, when the system runs in a circle, sinusoidal circle like this, I'm sure you've seen that. Most of the equipment love and maintain and keep this sign. The minute that you manipulate this sign, screw it up, all the relationship between the phases get screwed up. So when you put this through an electronic device, it ends up looking like this. Literally. The electronic device, the way they utilize electricity, they utilize it in nonlinear way. A nonlinear way means it screw up the curves from this shape into this shape. Who cares? Who cares about curves? Well, who cares? All the relationship between the phases will be screwed up. And you end up with a balanced three-phase system with a neutral still carrying the same amount of current as the phases. Don't worry, gentlemen. We solve the problem by doing the following, right? We have number 12, 4 conductors, okay? So each one of them will be number 12. The neutral will be number 12. 10 amps will not overload the neutral. And you're good to go. That's how they solve the problem. Okay? So that's why, so when you see they overheat the neutral, now there will be a situation, guys, especially in the data centers, where the neutral could be overheated if you don't take into consideration. So this is how we do the calculation, guys. Determine the connected load. Connected load. Connected load, guys, versus an EC code book. You're supposed to choose the largest of your design load, if you have a load, add the volt amp volume fixtures, lights, and add and go to the NEC code book, whichever is larger you're supposed to use. For example, if you're designing, your connected load is just adding the volt amp. Suppose I came up here with 1,000 volt amp, and this gave me 900 volt amp. Which one should I choose? 1,000 for lights. This is just as in the storage area. If you guys look at the table, 220.12 will get you 0.25 volt ampere square foot for your storage area. And you do, because that building is a storage area. Receptacle guys are allocated for 180 volt amp. All your receptacles are 180 volt amp per receptacle. I'll show you a couple of examples how they do them. This is how the receptacle load is basically encountered. Oops, not this Chad, this one. Okay. Look at this. This is how your receptacles is allocated load. If you have a single receptacle, can you guys see it? I want you to pay attention to this guy. How many single receptacle? This is called single receptacle. Okay? You allocate to it 180. If it's duplex receptacle, it's still 180. The minute they start quad, this is called quadruplex or two duplex. Two duplex or quadruplex, then it becomes 2 times what? 180, right? That will give you 360. And then if this is another quad looking like this, right? You've seen it. This will be the same thing, 2 times what? 180. So this, like, treating them as 2 duplex, right? And this is also 2 duplex. So when we say a receptacle, it means a one single receptacle 180, a duplex receptacle 180. A quadruplex, you multiply the 180 by what? 2. Cool. So that's how they do the calculation for that baby. All right, so we got that one. No, NEC receptacle, AC service, and the AC equipment guys are required. It was here. Your AC equipment is also required to have your AC equipment is required to have a receptacle within 25 feet. So if you have an air handling unit, chiller, whatever, you're supposed to have one receptacle, duplex or single, right within 25 feet. Anybody can guess why? Yes, service. The NEC code book does not allocate volt amp, so a lot of people use 180 volt amp, or some engineers use even more than that for that receptacle. We talked about these, gentlemen. Sign outlets. I talked about sign outlets last time. Just we did the math for it. We said 1200 volt amp for your sign. Here's your reference, and you have to have a 20 amp circuit for the sign, dedicated for that sign, and also you have to have some type of a disconnect means. So that's what they do for your sign. So what you do, you grab a 20 amp circuit, guys, right here, all the way to the sign. Here's my sign. This is welcome. And then they typically have a disconnect right here for safety. And when you size it best 1200 volt amp. Done. Every commercial building, the accessible, need a sign. The rest of the appliances, guys, motors and appliances, they have different articles that apply to them, and which we will be going over. Number one, appliances. Appliances like water heater, like your water heater, there will be an article 422. Can you guys put water heater? They're referring to this one. If your appliances have a motor on them, if your appliances has a motor, does the water heater has a motor? No. Water heaters don't have motors. If the appliance has a motor on them, they refer you to Article 430. 430 is the definition. 430 is what? Motors. Anything that has a motor. Heating element. If you're doing electric heat, guys, electric heat, here's your article 424. HVAC equipment, like chiller. And these articles, guys, any piece of equipment, they have so-called hermetic refrigeration motor compressor, which we'll be talking about this one, guys, in detail. Chillers. A good example of a chiller or AC unit, air conditioning and chillers. You have to go to this article. This is heaters, electric heaters. Can you guys see that the NEC code book takes certain things and allocate them to certain articles? Certain things allocated to certain articles. And I referred to this, guys, when I was doing my example. You guys remember we didn't use 422, we used 430, and we used 440 when we did the math. Hermetic motor compressor. Are you guys familiar with the Hermetic cycle? Okay, refrigeration cycle. How do they cool? The world was divided before the refrigeration cycle was invented and after refrigeration cycle was invented. Believe me, because there's a, if you read, there is a shift in the even in the U.S. Like the transfer of the power from the north to the south happened because the refrigeration cycle was invented. Now people can inhabit desert and live in southern the U.S. and the area that's really hot. That's because of that's how powerful the refrigeration cycle on the behavior of a human being. So long story short, it's a big deal, refrigeration cycle. What does it do, guys? You have to have a refrigerant, they compress it with a compressor, and then when they compress it, guys, and then they have blower that blows the air through it, it takes the heat out of that compressed refrigerant, throw it outside, and they circulate it to the inside. And the inside, gentlemen, it comes to the evaporator. The evaporator has a blower inside it. The same thing. It collects, take the air in your house, circulate it through these coils. They call them the coils. It collects the heat. The heat transfer from the air to the coils, from the coils to the refrigerant inside them, and they shove it all the way back to the compressor. They compress it, and they have big blower outside, blows the heat out, and they keep doing it over and over and over again. And again, we'll do that one industrial, guys. We have a whole lot of stuff about it. Anyway, because of the special requirement for that guy, the Hermetic compressor, guys, we have a supply voltage, we have the refrigerant compressor motor, we have evaporator, and we have condenser. So when you have a heating cooling system, there's multiple things working together. You're going to see them in a second. Here's how it looks like, gentlemen. In the inside your house and mine, this is what you have. This is for a commercial building. On the outside, that's what you have. Two different units coming from two different circuits. Outdoor, you have the compressor. Here's my compressor refrigerant, and condenser fan. So now you have a refrigerant that is very pressurized, very high pressure. The reason why they make it high pressure is because when they blow the air through the coils, it's easier to pick the heat out of the coils, which is coming out of the refrigerant. So now you're shooting the heat that you collected from the house to the Mother Nature outside. Now, where do you collect the heat though? This is you shoot it outside. The heat is coming thrown out. How do you collect the heat? You come here, the indoor unit. The indoor unit, guys, comes they call it the evaporator here. So the evaporator, this guy pulls the air through the evaporator coils, the inward coils, and the coils will collect the heat, send the heat to the compressor, and with this condenser fan, throw it all the way outside, and they keep doing it over and over again. Anybody can tell me what this is doing here for living? That's your heat, because it's a heat cool system. So if you're not cooling, then you heat. It's if you're not cooling, you're heating. It's called split system, guys, because it's two units. Typically, do you guys have how many? May I ask how many of you have central air? Central air heating and cooling. If you have central air, that's exactly what you're doing, except it's not three-phase. Your house and mine, this is three-phase. It's exactly how central. You have the central air sitting outside. You have and we don't heat. My house is natural gas instead of electric, so I don't need this. If your house is natural gas, you typically this one. What happened to this? You don't heat with. You said you guys are electric, right?
Yeah, solid state and natural gas.
Yep. So dual system. So if you're electric, you'll have the heating element. If you're natural gas only, you don't. So anyway, so when you calculate all these, can you guys see there's a lot of horsepower, blah blah, have to be calculated on this system. Then they're walking you guys. For this one, I'm gonna walk you through just the air conditioning here. There's an example, and that's because they're walking you guys through example here. Oops, there you go. Okay, talking about. Here's the air conditioning. I'm almost done. I know it's Monday, guys. We're waiting for our friends here to travel. So let me just, I want to explain to you guys one little thing. You're going to hear all the time, that damp location. This is how they define the damp location. 45-degree angle. So guys, can you see the 45-degree angle here? 45-degree angle it will create a damn location. Anybody can tell me what's the location here, right at this point? Wet. So if you have an eave like this, right from the eave, 45 degree down, that angle will create this area. Anything here, it has to be rated for damp location. If you put your lighting fixture here, your fixture have to be rated for what? Wet location. Who cares? Most of the fixtures, guys, are rated for wet location that can be installed all over. So, but be aware of wet versus damp. Okay, weatherproof. Weatherproof receptacle, guys, you're required to have an outdoor receptacle, weatherproof in-use cover. You can see the bubble. So when you put your receptacles on the plant, I expect you to have next to them say weatherproof, meaning after 5 years, when you try to take the receptacle out, it's not going to fall in your pot. It's made to robust. They call them weatherproof receptacle. Then in-use cover. Do you guys see these bubbles? They have them. Extra hard usage bubbles, so you can plug in and at the same time cover. That's required for all wet location receptacles. Residential, commercial, doesn't matter. So that's where they put the weatherproof cover. So this guy here, this cover here will not cut it. The cover that you need right now is a bubble like this. And it has to be hard usage. It's not that plastic little thin one. It wouldn't cut it in 2014. That was changed also in 2014. Metallic will always cover it, but they do make plastic, thick, solid plastic that they cover. So the old ones that used to push it with your hand and you can bend it, that wouldn't cut it anymore. Change in 2014. Wait until 2017, we'll do something. We talked about this one, guys. Here's when you have a hermetic motor, guys. You have an nameplate like this. And we will talk about these guys a lot when we move on to so look at the nameplate. The nameplate, guys, will give you the voltage. Can you see the voltage right at the top? It gives you the compressor, rated, can you guys rated load amps, the condenser, horsepower and amps, evaporator, and then the most important thing is this values. So minimum branch circuit selection current, the fuse, as well as the hamper breaker. So from here, conductor, and from here, this is circuit breaker or fuse, from these two, or fuse. So long story short, for HVAC equipment, guys, they tell you exactly how you're going to size it. You don't have to do any calculation. And we'll talk about this one a lot as we go. So this is my HVAC equipment, the compressor, as well as the evaporators, compressor rated load amps. So here's the table. You guys are looking at that table. You're familiar with that? So I'm not gonna. Okay. This table is related to the actual lighting load. So please pay attention to this one. Remember, we have a project in this book has a project. So whom am I going to pick on? Alex. Alex, my friend, decided to put style 1 fixtures, 27 of them, and each one of them is running at 61 volt amp, predicted load, right? So you take 27, multiply it by 61, this is what you get. Is it continuous load? These fixtures, they're assuming these fixtures are non-continuous load. That's what they're doing in this calculation, assuming they're not continuous load. Typically, we do assume it's continuous load. Okay, everybody understand what type G emergency, type E2, type E, and E emergency, all these fixtures, guys, and exit signs, these are nameplate values, not any secret book. So, Jay, you add them all up and you compare what any secret book can give you and choose what? The larger of the two. That's what, you guys are going to do the same thing for our commercial project. You're going to take the volt amp of all your fixtures from the manufacturer, compare them to the 3.5 volt amp, choose what? The larger. And I can tell you from now, anybody can guess what the larger would be? The code book. Almost always. Because you have to meet the energy code. You know, you can't just go put any fixture. Okay. Luminaire connected to drugstore. These are the luminaires in the drugstore. This is just, guys, the different type of luminaires and the volt amp for them. The last one that they have for you here is this load calculation that they did. If you guys allow me just a few seconds here to walk you through how they do it. This is the load count for the project. Very easy, very simple. Everything is simple for you, Jen, huh? Here's your general load, general lighting. Can you guys focus on this? General lighting. How many, the count, how many fixtures in the square foot? This is your square foot. I have this amount of square feet multiplied by 3. That will give me this. Can you guys see that? This is 1395 square foot multiplied by 3, give you this value. Connected load. Now, anybody knows where the connected load coming from? Where is this number coming from? The table that we're just looking at. That's all the fixtures, adding all the fixtures for this place. This is actual. They call it actual. Okay, now, Jay, you're comparing the code with the actual. So which one are you going to choose? The code. That's what they're doing. Can you guys see that? Exactly what we did, except they add the actual. All right, let's go to the second one. Underneath it, the storage area. We have a storage area. The same thing, guys. Here's your square foot. Multiply by this, equal this. Here's the connected. Here's the connected. Here's the actual. Which one is the largest? In this case, the actual is larger, so we use the actual. You choose the larger of the two. All right, go. So then you add them up, basically. Other loads, receptacles. I have 21 receptacles. Multiplied by 180 give you this. They are 180. That's by code. Copy machine. The copy machine, guys, they're assigning. Now, here's what something going to confuse you, Gary, my friend. Where the heck are they coming with these numbers? Like copy machine receptacle 1440. Design criteria. That's from the equipment that you're going to plug in. Can I just get you to don't get confused here? They have, for example, I have a copy machine. I have a receptacle for HVAC. A sign. The sign we know where it came from. The cash register. The electrical door. The water heater. All this, the unit heater. All these values, guys, where did you get them? From the specification, not the code. The only one actually from the code is the 12. This one is from the code, right? NEC code. The rest, can you see? And all of them are from the owner. The owner is telling you these are the equipment I'm going to put there, and these are the voltage. Okay. So that's and you add them up. Can you see? You add them all up, and you put them in here. Unit heater, water heater, unit heater storage. Then you get the last thing, guys, is the AC unit. Your AC unit, we're giving you the AC unit as the amps. Here's my amps multiplied by the voltage. Get you this amount for the indoor unit. The outdoor unit, you're given this amount for the outdoor unit, and the exhaust fan, this amount. You add them all up, and that's your total for the whole continuous. Oh, if they're continuous load. Look what they do. If they're continuous load, guys, they put them on their continuous and they multiply them by 1.25 at the end. And finally, my friend, and they add the neutral too. Can you just see that they're neutral? They're adding them on the neutral and they're putting it with their continuous load here on the neutral load, like we did, and continuous load or non-continuous load. Because what's the difference? The continuous you multiply at the end by what? 1.25. All the way into the end, gentlemen. And they came up with this number for the phase, this number for the neutral. Your neutral size based on they divide. This number is divided by 208. I think it's that the voltage. Can't remember what the voltage is of that system. We're just looking at it. Short memory. Yeah, thank you. It's a 208 multiplied by 1.73. So divide this number. That's what they came up with these numbers, guys. Divide these two numbers by 2.8, and they came up with 138.2. Now, what's the service size for this building? If it's 138, what's the next standard overcapacity device? 240.4.6. The standard overcurrent protection device. So take this number and go find yourself an overcapacity device. 138. 150. Yeah. Now they might size it for 200. Will it be wrong? Remember, it's the minimum. That's it, gentlemen. That's the load calculation for this. In one No gimmicks, nothing. And they have the notes how they did it. So please, between the example I gave you guys, this chapter, and the template I'm going to give you, hopefully that will give you a complete full picture of what the commercial load calculation. And if that's not enough, we're going to do the residential too. Okay, so we have guys, what time is it? Yeah, take a quick break before those guys come up. Thank you. I believe so, yeah. It's that. Might have to make more.